Okay, so the situation that we've got here is a beam supported by three posts, A, B, and C. The outer ones, they've got a diameter of 60 millimeters, and they're made of a material with this Young's modulus, 70 GPa, and a yield strength of 20 MPa. The middle one, it is a stiffer and a stronger material, so it's got a Young's modulus of 100 GPa, and its yield strength is a whopping 590 MPa. And then if the loads applied there are 130 kilonewtons, we're trying to figure out what the diameter of the post B is, such that all three posts be about to yield. So setup symmetric, so we don't need to worry too much about the distribution of the forces. So if we know that A and C are about to yield, then we know how much, we can find out how much force is applied to them because we know what stress is being caused in them. So stress, is going to be force over the area. Force over the cross-sectional area. So if we know what the yield strength is, and we know what the area is because we know what the diameter is, we can figure out what load those things are carrying, what portion of the load those things are carrying. So just plug those numbers in, 20 MPa times pi times radius squared, so diameter divided by 2 squared, gives us 56,520 MPa times millimeters squared, which again just cancels out to newtons. So 56.5 kilonewtons. Here's a little free body diagram of the beam again. So simple enough to just figure out what our one unknown there is. We sum the forces in the y direction, and we get ourselves a force from the post B of 147 kilonewtons. So then moving on, so we know that the stress in B needs to be the yield stress, which will also be equal to the force that we just solved for divided by the area. So we can rejig this equation to solve for the radius of B there, and then I just rejigged it again, multiplied by 2 here to solve for our diameter instead. Plug the numbers in there. 147,000 kilonewtons divided by pi times our 590 MPa. Again, MPa divided by newtons will cancel. Newtons divided by MPa, the newtons cancel out, which will give us MPa squared. This will cancel out here to millimeters squared, which when we take the square root gives us millimeters at the end here. So our units cancel out nicely and give us a diameter for that rod of 17.52 millimeters, which is substantially less than it's about a slightly less than a third of the diameter of the posts on the other side, but that shouldn't be too surprising because the yield strength that we're working, the yield strength is a lot higher than the yield strength for B is going to be a lot higher than the yield strength for A and C. So it needs to be kind of concentrating that load in a larger spot. Even though it's taking more, even though it's taking more than half of the total load being applied, it's just that much stronger at 590 MPa versus our 20 MPa for the posts on the other side. These are weak and spindly little. Oh, sorry, they're fatter. They're not spindly, but they're weak. They're weak and feeble, so they can't carry nearly as much load as the B1.